some of the technology solutions, and then I'll summarize. So we were just, I was just at Mobile World Congress a few weeks back at the end of February, and it was a very, very exciting show. One of the things that we saw were all of these different topics were discussed in some way or another at the show. But foremost, and clearly on everyone's mind, if you went to all the different booths, someone had something about 5G, whether it was hardware, software, some way to control the network. It was very exciting to see, which made it very real for at least for me, as it related to going to the show and seeing that 5G was in fact advancing its deployment, and many customers and many providers were getting ready for the deployment of 5G. So clearly something on the horizon, and we saw a number of different announcements that were made at the show as well. Particularly out of China. Personally, I feel that China is very much ahead of some of the other regions in terms of deployment and adoption of 5G. And we clearly see that in some of the announcements being made by Huawei and China and China Mobile with respect to their partnerships with various entities in the industry to bring 5G out and make it successful. So why is 5G exciting, and why in essence is it very important? And I think one of the things I just want to maybe flash up here is at this year's Mobile World Congress, there was a big focus on sustainable development, the UN Sustainable Development Goals, and really the point of these goals is developing a 17-point plan to really improve the betterment of society and humanity. And you see many of these goals listed here, like no poverty, zero hunger, or gender equality, and all of this being prompted by the advancement of communications between people. And it really, we're really seeing that 5G is that culmination of communications capability that will help bring about some of these global goals. So as you think about your everyday work and see what you do in your everyday life, keep some of this in mind as you develop your next radios or your next products for the 5G network. So 5G comes with great complexity and cost, unfortunately. So in order to create the capacity and the type of data rates and the user experience that is going to be needed, or that is promised by 5G, we have to overcome a number of different hurdles and do what may potentially be unnatural things in terms of architecture and getting around some of the challenges around enabling these 5G communications. For example, with 4G LTE, we certainly saw the increasing number of bands that had to be deployed, and that's also going to be the same issue that we will have to face in 5G. The implementation of massive MIMO to be able to implement very high data rate communications to specific groups or users using this type of method, which increases the complexity of the antenna system in 5G. Continued adoption of carrier aggregation. So we've seen carrier aggregation evolve over time as part of the 4G standard, and that will continue on as we get into 5G new radio. The implementation of carrier aggregation to basically increase and aggregate data rates. Probably two of the more controversial issues is as we get into these much more complex waveforms. As we get into 64 QAM, 256 QAM, and even some of the higher order modulation rates, this really puts a strain on linearity, particularly in the PA and some of the front end circuits, in order to be able to solution, in order to keep the signal as linear as possible over the entire range. And what this has an impact is this peak to average power ratio. What we see is in some of the newer standards that the peak to average power ratio is almost on the order of 11 dB, which is almost 2x the peak to average that we saw in 4G LTE. So this places much more strains on the PA and being able to back off the PA to make sure that it remains linear over the entire signal envelope range. And then finally, the implementation of phased arrays and even getting up to millimeter wave frequencies. I think this is an area that is not new. These are systems that have been implemented by the military, over many years, and now being used for commercial type of applications, consumer applications, to really bring about the type of user experience and data rates that we've come to expect through 5G. So let's step back and see, well, how will radios evolve as we go from 4G LTE to 5G? Well, in 4G we had a small number of antennas. The frequencies were very manageable, very low bandwidth type of systems. You basically had a discrete PA or a single PA that had to put out very high output power in an isotropic radiated fashion. As we move to 5G, now we start to look at things like the implementation of massive MIMO. So we have a number of different beamforming antennas that create a specific a signal beam to a particular user. We now operate in very high frequency. Now we're into the millimeter wave regime. So the design techniques and the design implementations at millimeter wave are much different than they would be, let's say, at lower frequency. High bandwidth systems now compared to low bandwidth. You now have a distributed PA system versus, say, a single PA that puts out high output power. And this distributed PA is the type of PA now implemented as part of these phased array antennas, where you have many PAs delivering power to individual elements in an array to basically create the beam. And then that necessitates some type of integration scenario, some type of way to integrate these PAs on a single chip. So I think what we'll see is clearly a shift, a paradigm shift in the way in particular the front end module and the radio in a 5G device will evolve. Just to set some context with respect to where we've been and where we're going. If we look back to, say, 2009, 2010 timeframe, radios were very simple. We only had to support maybe a maximum number of 4 bands. The radio itself was very simple. As we moved to 3G, we got a little bit more complex. We started adding more switches, more filters in the front end, more PAs in order to handle the number of bands. Then as we got into LTE and into LTE Advanced, the complexity skyrocketed. We started getting almost exponential increase in the number of filters and the number of switches and the number of content that was in the radio. Back here, we were probably talking about less than $2 for the entire front end. Over here, we're now starting to talk about on the order of $20, $25, almost more than what the baseband costs in terms of the amount of content that has to be integrated and made to perform to support LTE Advanced. And we believe that's not going to stop as we get into 5G. There are some estimates that indicate that the radio will actually double in cost as we go into 5G, and that's going to prompt us to be able to develop technologies that can not only drive the cost down, but get higher levels of integration in these types of systems. So let's talk a little bit about the phased array and what really drives the phased array. And one of the important elements, if you've been following many of the stories and many of the papers closely, is that there's this this device called the beamformer front-end module, and this is really the heart of creating the steerable beams in a 5G either sub-6 or millimeter wave type of solution. And there's various ways to implement beamforming. And what I've done here is I've listed the three approaches that today are most prevalent as it relates to beamforming. The first we have is analog beamforming. Analog beamforming is done just as it says. It's all analog. There's really no digital control per se in this type of beamforming. All of the phase shifting is done with analog signals. Everything is up converted from IF to RF. It tends to have the smallest number of components, also the lowest power dissipation, because the ADC is basically operating at IF sampling. But it's most sensitive to interconnect loss, because now you have RF frequencies that you have to, RF or IF frequencies that you have to route and be careful with as you route them around the phone. And there's also some complexity in the phase shifting. So the phase accuracy between these analog channels, between the LNA, the PA, and all the different beams that and different streams that you have here has to be pretty accurate. So a lot of that comes at the cost of doing some processing in the baseband. There's also the second type of beamforming, which is all digital. So all the beamforming is done digitally. So all the phase shifting, all the pre-distortion, all of it is done back here in the baseband through the ADCs and DACs. However, the challenge with this is that it does drive a large number of components, and it has very high power dissipation. And the reason it has very high power dissipation because these ADCs and DACs need to operate at very, very high frequencies in order to be able to keep up with the modulation rates that are supported by 5G. So very high power dissipation. So one of the key requirements here is selecting a technology that can deliver very low power, even at high frequencies. And then finally, there's this hybrid beamforming scheme. So this is basically the best of both worlds that takes both digital beamforming and analog beamforming and combines it in a fashion where the two can work together to optimize the performance of both the digital processing associated with digital beamforming and the analog processing supported by the analog beamforming. This tends to be used, or at least from what we've seen, for large arrays where the analog and digital beamforming are inefficient and complex, particularly for some of these small arrays. For example, you would not want to use digital beamforming in a very large array. You're talking about many ADCs and DACs that are operating at very, very high frequency, so the power dissipation is going to be very, very high. So by having a combination of both of these, you can achieve the type of power consumption that you want for some of these very large array applications. So what we see in general, from what I summarized here, is that analog and digital beamforming will likely gravitate to the UE and small cell type of applications, and then we'll see this hybrid beamforming be mostly focused in base station applications where you do have to have large phased array antenna type of systems. Let's talk a little bit about the UE and this beamformer module. This was taken from a recent IEEE paper that I found very, very interesting that showed this 2x4 beamformer module with how it might be assembled. Obviously the incident power, the incident signal on the top layer where the phased array antenna is. This is where all the millimeter wave. This is where the millimeter wave interface is. So you want to keep the distance and the interconnect between the phased array antenna and the active circuits very, very short in order to make sure that you minimize the losses and the mismatches at millimeter wave frequency, because designing at those frequencies is very, very tricky. So the idea would be to get from millimeter wave to IF frequency as quickly as possible in this scenario, so that you can then route the IF frequency to, say, a transceiver or baseband chip inside the handset somewhere that may be located. So this beamformer module would process all of the transmit and receive, do all of the transmit and receive signal translation for 5G and support, in this case, the millimeter wave. And you can see that this beamformer module could be placed anywhere on the periphery of the handset in order to be able to support the type of beamforming and steerable beams that would be needed in order to ensure that no matter how I am oriented, I can always find a base station or a small cell that I can connect to. And these steerable beams would be always actively steering to find and connect to the base station. So this is an interesting aspect, and probably what we will see as first generation type of beamformer systems as 5G rolls out into the marketplace. But if we talk a moment about sub-6, there's certainly some challenges associated with implementation of new radio. One of them, for sure, is the desensitization that may come from utilizing a minimum number of antennas. For example, coexistence of the 4G radio with the 4G LTE radio and the 5G signals will create nonlinearities that mix together and create descent signals that will fall into the receive band in some combination pairs. So it's important to be able to mitigate those types of situations by implementation of separation techniques so that we minimize that type of interference. So in this particular case, one of the approaches that has been discussed is actually, instead of utilizing a single antenna to combine and potentially create nonlinearities that create IM, actually move to a dual antenna system where the interference is not completely eliminated but minimized in order to support the radio performance needed in those bands. One of the other issues that we see as well, and this is really a part of millimeter wave operation and really delivering power at millimeter wave frequencies, is obtaining the type of efficiency that's going to be needed at the PA to support millimeter wave. And this chart shows what the differences in temperature rise could potentially be for a given array, let's say, depending upon the type of efficiency each of the PAs in the array may have. And what we find is that certainly if you're not operating at a very high efficiency, the temperature rise associated with power lost as heat is dramatically different than if you have a PA that operates at very high efficiency. So one of the key messages here that we need to remember is that as we go forward, that having a set of technologies that not only can integrate, but also can provide and support very highly efficient PA operation for millimeter wave signal generation is going to be very, very important. So something to keep in mind as we go forward and look at how we implement these beamformer modules. So at Globalfoundries we've taken a look at some of the key technologies that would be candidates certainly for helping to solution some of the beamformer and transceiver systems that are out there today. And quite frankly, what we feel is, between, say, RF CMOS, which is obviously the most prevalent technology out there, many nodes availability down to 22 and even 14 nanometer FinFET. Silicon germanium also has another technology, and again, this is really a silicon technology statement. We really feel that SOI actually provides the best balance of being able to have the most flexibility to be able to design the type of elements that are going to be needed for 5G millimeter wave operation. And many of it comes at the ability to have very high FTF max, the ability to stack devices, the ability to have very high performance back end of line characteristics where you can do things like transmission lines and high performance, high Q inductors. The availability of things of high resistivity substrates, the availability of fully depleted substrates where you can now get access to the backgate bias for doing tuning and calibration, particularly very important as we move into millimeter wave. So much of the focus that we have today at Globalfoundries and many of our customers are looking at is the implementation of some of these 5G millimeter wave systems in SOI. So at Globalfoundries we have two specific technologies that are based on SOI that we see very prevalent and really making a mark in terms of separation on where you would use one technology over the other. And if we look at a typical beamformer lineup, we would split this up in two ways. You have You'd have certain approaches that would be very, very FEM-centric, that would locate the front-end module, say, in a particular area of a handset or a device, that would route the resulting IF to some place on the board. This is what we would call a FEM-centric approach, and this is very, very much aligned with our 45 RFSOI technology that has been built to support very high FTF max, supports very high substrate, and has been proven to, and I'll show a little bit later on, to develop close to 25 dBm output power per element, has the characteristics of low loss, and also can integrate some amount of logic as well for those types of systems where you need logic. Then there's the integration-centric designs. These are the integration type of approaches where you're gonna integrate everything on a single chip: the radio, the beamformer, the radio transceiver, the baseband, all on a single device. We really feel that 22FDX is that type of technology that is that's really needed for these types of systems. Again, has some of the similar characteristics, but it has the advantage of very low power and very high levels of integration because of the high density logic in 22 nanometer. So we just recently announced 45 RFSOI. I'm not going to dwell on that, but we just recently qualified this technology and is ready for production. We have a number of customers that we've engaged and are in the process of developing and deploying systems. And some of the key aspects of this technology that are really, really important are the availability of high linearity, the low substrate loss that I talked about, the ability to do device stacking, much like we do today in RFSOI, very high FT, high F max, and very very good back end of line, all copper back end with thick metals to be able to do the transmission lines and inductors that are needed for this system. This is some of the performance metrics that we've been able to demonstrate between PA, LNA, and switch, and that's what we see as the fundamental elements for developing a beamformer module. You have to have a PA, or ability to integrate a number of PAs on a single die. You have to have a very good LNA, and you have to have a very good switch. So these are some of the results that we've received. We have an internal pathfinding team that's been doing a lot of work, and we work with a number of different partners as well, universities, et cetera, and academic institutions that have done a number of designs in each of these different areas. And you can see some of the performance. And what I want to call the attention to is the PAE that we've been able to achieve at PSAT. This is quite remarkable, the type of efficiencies that we're able to get. And again, keep in mind, this goes back to what I discussed earlier about making sure that we optimize the efficiency of the PA so that we don't throw away that efficiency as heat. Very good LNA performance and also very good low loss switch for implementation of switches. Now 22FDX, let me switch gears a little bit here on 22FDX. We'll talk a little bit about some of the, it's time to go? Okay, well, let me one conclusion, and then we'll get done here. So 22FDX technology is the technology that we've developed that is doing all SoC type of integration. One of the key advantages of this technology is the ability to do backgate bias tuning, backgate control to be able to manage power output and also calibration of the radio. And this is going to be important for millimeter wave. We've done additional pathfinding in this technology as well, and this information is available for you at the end of the conference. We've also developed this RF Wave Partner Program to assist customers who are developing products in millimeter wave. And please talk to us if you have interest in engaging us on these technologies. And then finally, I think I've talked much about what we're concluding here. I think it's very key that we have silicon technologies can be able to integrate the type of performance that's needed for millimeter wave. And I really think that the innovation that will come as part of this will be will really drive this market. So thank you. Apologize for going over. Thank you.